This is Chip Shearer, and I just wanted to welcome everybody to the Planetary Sample Science Seminar. And today we have a real treat today. We're going again beyond Earth and looking for the development of using resources on other planetary bodies. And it's my pleasure to introduce Maryam Hojati, who will be speaking upon building beyond Earth, pioneering the future with additive manufacturing and space habitats. Miriam, take it away.
Thank you so much. Could you see my slide here?
All right. We see the first slide.
Yeah, that's perfect. Hello, everyone. My name is Maryam Hojati. I'm assistant professor in the Department of Civil Engineering. I did my master, PhD and postdoc at the university at Penn State University, and joined UNM in 2019 as an assistant professor. I established Advanced Sustainable Construction Lab, and currently working with a team of undergraduate students and graduate students on different aspects of addressing construction material and practices for future of this industry. So here is a picture of me where we were in a head-to-head NASA Centennial Challenge in 2019 with my advisor and some of my colleagues at Penn State. This was part of NASA Centennial Challenge that I will review part of the thing that we did over this competition, NASA competition for 3 years at Penn State. This head-to-head competition take place at Visitor Center of Caterpillar in Peoria, Illinois in 2019, and our team were able to achieve the second best place in this competition. And this is me. All right, so this is the outline of my presentation. I will start by reviewing the new advancement in construction industry. So I know some of you might not be familiar with the new advancement that we have in the construction industry. I'm going to quickly review that, and this is part of the research that I'm currently doing at UNM. The second part is all about the NASA Centennial Challenge. This was part of the challenge that I did during my PhD and postdoc at Penn State University. And I'm going to review different phases of the challenge at the UNM, at Penn State, sorry. And the last but not least, I'm going to quickly review some of the future plan that NASA has for construction in space. So I'm gonna start with the first topic of my presentation, which is about the new advancement for the construction industry. So currently, nowadays, about 1 billion people are living in the unhealthy and substandard condition around the world. Over the next few years, up to 2050, about 2.5 billion other people are projected to migrate gradually into cities and urban areas. So with this rapid urbanization, with the climate change, with the shortage of the resources, the demand for dignified and affordable housing and also infrastructure for this population just increase over time. In this slide, I'm going to review to see if the current construction industry has the capacity to address this high demand for affordable housing and infrastructure for the future. So construction industry has very large impact in the world economy. It's worth about $10 trillion or 13% of GDP globally. But this industry has suffered for so many years for low productivity. While other sectors of industry like agriculture or manufacturing, they are increasing the way that they are producing material and goods over the last 100 years, over the last century. Construction industry almost remains in the same stock over the last century. So One of the main reasons behind this low productivity in this industry is that it largely remain manual. So most of the construction process is manual. When the COVID started some few years ago, it was one of the industry in big danger because social distancing doesn't make sense for this industry. It has been done by laborers, it's highly labor intensive, and it's hard to be able to do the construction without having the manpower. So this is one of the reasons behind the low productivity in this industry. And while other industry like agriculture or also manufacturing, they try to adapt the new digital and new technology and sensing technology in their fabrication. Construction has some conservative approach to adapt this new technology and improve the way that they are building the construction. And I'm going to review some of the important problems that our current or conventional construction industry is suffering. First of all, it's very slow, and the reason is that it's highly labor intensive. It's not a safe operation process. In this country, it's about 10,000 people killed during the construction process every year, and 400,000 are injured during the construction process because it's not really safe, it's highly done manually, and it results in such a dangerous work environment for the laborers. Because of the involvement of so many trades in this industry, it's highly prone to corruption, and always the construction is over budget. So you need to keep adding budget to be able to finish some construction project at the end. This slide shows one of the reports by McKinsey institution. They just monitor the productivity in the construction industry, in the total economy, and also other manufacturing industry in 20-year time window. So as you can see, in 20 years, the construction industry has just 20% improvement in the way that they are producing the buildings or constructing the buildings, while the total economy had 70% increase, and the other manufacturing almost double in 20 years or 2 decades time window. And it means that the construction industry just has 1% improvement in terms of productivity per year, while other industry like total economy has 2.5% improvement, and other manufacturing has almost 4% improvement per year. And again, all of these things return back to the low productivity of this construction operation because it has been done largely manually, while other manufacturing industry try to adapt the new technology or processes for their operation to fabricate material and tools. So humans were able to address the low productivity issue through different industrial revolution over these years. So industrial revolution helps the human to address some of the productivity issue over the last 300 years. Whenever the human find a way to fabricate more product and goods for larger population with lower cost and also improve the standard of the living for larger population, they call it industrial revolution. And it changed the economy, which was mostly dependent on the agriculture and handicraft, to the economy, which is nowadays based on the big factories, the big mechanized system, and also large industry. So it has started with the use of the steam and water power to increase the speed of fabrication. And then the second industrial revolution that took place about 150 years ago was all about the use of electricity and the assembly line. The third industrial revolution was all about the use of computerization and also automation for the fabrication process. And if you, I'm not sure if you are aware or not, we currently live in the fourth industrial revolution, what we call it Industry 4, and it's all about the cyber physical system, Internet of Things, and Internet of the System. And in the simple word, it means all of the big industrial part are augmented with the web connectivity to a central system. The central system could visualize the entire production process, and it could make decision on its own. So this is what we call it, the fourth industrial revolution, and it has high potential to improve the way that we currently produce products and goods for the population. So by the right use of this new technology in Industry 4, construction industry could make changes in the way that we are building the construction, the infrastructure and housing for our population. So the new technology, the new industrial revolution could reshape the productivity in the current industry that we have. And one of the most important area that could be used in the construction industry is all about the 3D printing. So 3D printing is all about how we can make any physical object from a digital file. So it's all about the layer-wise deposition of the material to form any physical object. And it's one of the main part of the third industrial revolution, and in many different fields of industry, including aerospace, including energy, biomedical, it gains so much popularity, and it has been used for so many years to 3D print different parts and goods and products by use of the digital and new technology. So 3D printing is all about making a digital geometry, any geometry that we want to make, a 3D geometry, and then from there we should slice it, because we talk about the layer-wise building of any physical object, then translate the file, the CAD file, for the printer and machine. And finally, the last step is just about producing and building the layer-wise deposition of the material to form the final 3D physical object. So this is all about 3D printing. And as I mentioned, it gains so much popularity in different fields, like in bioprinting, the firms are working on printing different body parts, different organs. In the energy, in the automotive, they are just printing different parts of the cars. So there are so much attention in the use of 3D printing. However, again, construction industry has some conservative approach to adapt this new technology. But if we can use this new technology for the future of this industry, we can address the slow productivity in this industry, we can improve the quality of the built environment, we can address the safety for the laborers. We can train new laborers who are working with machine instead of working in the field and directly deal with different dangers that we have in the construction industry. So there are high potential for adoption of 3D printing in the construction, but as I mentioned, compared to the other industry, there are some conservative approach to accept and adapt this technology for the construction industry. And one of the hesitation behind using this type of construction is about the scale. So when we talk about bioprinting, we talk about tiny body parts, which is much more manageable when it comes to the system or printer. But when we talk about printing a house, printing an infrastructure like bridges, the size of the system should be much, much larger. And the number of problems which come along with the larger scale would be much, much higher compared to other sectors of industry. There are so many trades in construction industry, and they have resistance to accept any efficient change for the way that they are constructing their buildings currently. The lack of trained and technical workforce, this is something that the academia and universities could make some change for the future of this construction industry. And also some of the difficulty that we couldn't use the conventional material that nowadays we are using for the construction industry, for the 3D printing industry. We need to use a special material adapted for construction. We need to come up with new codes and standards that bring safety for the structure or building which is 3D printed. So these are some of the important factors that provide some hesitation for adoption of this new technology in the construction. But currently, especially over the last 5 years, there is a very fast approach between industry and different research teams to speed up the adoption of this new technology in the construction industry. Some of the material that has been so far used is concrete. However, this concrete, which is used for 3D printing, is completely different than conventional concrete. There is no formwork for this structure. It could self-sustain the weight of the material in the fresh stage. And because of that, there are some important technique that we should consider when we are dealing with the design of printable material. Other than concrete, some local resources like local soil has high potential to be used for construction of 3D printed structure. One example is shown here, which is just 3D printing of local resources to make this house or this shelter. And by using of this new technology, we are able to 3D print any curvilinear structure and take the advantages of structural advantages of this type of structure, which could hold higher amounts of load and have better resistance against different types of load. So some of companies currently in the United States and other countries are using this new technology. Some of the companies listed here, the number of this company is increasing from day to day currently because they found it really interesting and there are good funding behind using this technology. Some of the companies that I listed here are US based, like Episcore, Icon, or Control Crafting, and some of them are not. Some of them are in China, in Europe country, or in other parts of the world. But I want to show you some of the examples of 3D printed house. This is the house, two-story house, which was printed in 2019 in Belgium, and they show that by using this new technique, they are able to finish the construction of two-story house just in 2 weeks. They have 60% fewer resources in terms of material and energy, 50% less carbon dioxide. The material that they designed and used was 3 times stronger than conventional material. One person was just monitored the entire construction operation during the printing process, and they show that there are high potential for using this technology for the construction. In Dubai, there is a neighborhood that they are 3D printing by collaborating with one of the US-based company, Episcore. And they're going to finish most of this construction by the next few years. In France, they are going to print an affordable houses for different communities. And also in Mexico, one of the US-based companies called Icon, they also 3D printed a fully neighborhood by use of this new technology. And these are some of the examples. If you check the media, you can see even larger example nowadays because there is very fast advancement in the adoption of this new technology in the construction industry. And other than houses or buildings, we can use it for different infrastructure. One example is for the wind turbine. So the old wind turbine are all, the conventional wind turbine are all up to 100 meters tall. But by using this new technology, we are able to achieve to higher level or taller wind turbine and get higher current, higher wind current and get higher energy from. So General Electric is just investing on this new technology to see if they could achieve better performance in the wind turbine and the way that they are producing power from these natural resources. Some of the examples for the application of this 3D printing technology is also listed here. The first is emergency housing. So whenever we want to have fast construction for those who are the victim of man-made or natural disaster, this is the best technology. As you see, in less than a week or 2 weeks, we could have the final building ready for the residents, so they don't need to wait for a long time to have some shelter for them. It could result low-income or affordable housing for so many people because we are lowering the cost for the formwork, for the labor, for the material and energy, and it could also address some of the environmental aspect that we have in the construction industry. It enables us to 3D print functionally graded material, the material that has different function at different parts of the three-dimensional object that we printed. And the last not but least is about the space colonies. Wherever there is no human or labor to take care of the construction, we can train robots and 3D printer to do the autonomous construction and build up the habitat for the space project. And the rest of my presentation, it's just about the application of this new technology for the space colonies. So in the second part of my presentation, as I mentioned, I'm going to review the NASA Centennial Challenge. It was a multi-phases challenge that NASA designed to just speed up the adoption of these new technology, 3D printing, for the Earth project and learn some experience to adapt it for a space project where you don't have enough human or labor to do the construction. So because it was part of the project that I did during my PhD and also postdoc, I'm going to just very quickly review some of the work that we did for this project. So there are so many arguments for and against space colonization, but one of the two most important ones, which are all in favor of space colonization, is all about the survival of human civilization within the event of planetary scale disaster, natural or man-made. And the second one is the availability of resources in terms of material and energy of the Earth. So there are so many researches going on around the world between different countries to speed up this space colonization. And Professor Hopkins also predicted that the human race would be extinct within the next 1,000 years. And if we don't find a solution for this problem, we're gonna just face the long-term extinction of the human race because of the way that we are using all of the resources because of the population which is increasing from year to year, and we need to find extra resources to address all of the need for these human and civilization. So there are two options. First is colonizing the space within the next 200 years and make residential units on other planets. Or the second one, if we don't do anything, we might face the prospect of long-term extinction over time because of the way that we currently using different resources from our Earth planet. But it's very important to know that we have endless resources in terms of material and energy when it goes to space. Our solar system by itself has 1,000 to billion times larger resources in terms of material or energy compared to Earth, whatever we have currently in the Earth. And because of that, the NASA administrator identified the space colonization as the ultimate goal for their current spaceflight programs. And there are so many different research going on about how we can colonize a space gradually over the next 200 years. So our solar system by itself has so many different resources that we can get material or energy. The inner planets have similar system as the Earth. So Venus is the closest one to the Earth in so many ways in terms of gravity. Mars has so many surface conditions similar to Earth, has great potential to be considered as for the colonization. The asteroid belts are also has enormous energy and material, and there are so many researches going on to see if there is a way that we can extract this material and energy for the Earth application. And also other planets, the satellites or natural moons of those planets which are all made of gas, could be also provide some extra resources in the other side of the solar system. So as you can see, there are so many areas of the research, and NASA is just focused in some specific locations for the space colonization that start with the moon as the near Earth space. So Moon has high potential for the space colonization because the proximity to Earth. The inner planets like Mercury, Venus, and Mars, they have also high potential. They are made of solid material. They have the highest solar energy, and they could provide great resources for the colonization. Asteroid belt is another option. And finally, the moon of outer planet, like moons of Saturn, are also some location that NASA is currently studying and see how we can find the way to get more resources from all different locations that they are just studying over so many years currently. In terms of colonization, Moon and Mars so far gained the most popularity. So maybe the permanent human communities and settlement of the Earth was in most of the science fiction theme or movies, but currently with the advanced technology and also by considering the concerns about the civilization and human race, there are so many research going on about how we can colonize Moon or Mars for the future of the space project. So because of the proximity to Earth, the Moon has been seen as the most obvious natural expansion after Earth. Additionally, recently, because of the discovery of the lunar water, they found it much more feasible. However, when it goes to atmosphere, when it goes to gravity, when it goes to the temperature, there are so many differences, and it makes the colonization much more difficult if we want to consider all of these conditions. So currently, Artemis project is aimed for returning humans to the Moon and establishing the sustainable lunar presence on Moon. So they have so many different phases for this project to see if it is feasible to colonize Moon as the first and the closest location that we have to Earth. Other than Moon, Mars also has high potential. The surface condition and presence of water on Mars make it very hospitable planet compared to the other planets in their solar system. There are some similarity between Mars and Earth. First of all, the length of the day in Mars and Earth are very similar. One day in Mars is equal to 24 hours and 39 minutes. Because of the actual tilt is 25 degrees for Mars and 23 degrees for Earth. They also have 4 distinct seasons. And the length of each of these seasons is almost double compared to the Earth season, but it makes some similarity in some way that make it very hospitable planet compared to the other planet. And it's the reason that NASA prioritized this planet for the space exploration. But there are also some differences when it comes to the gravity. It has like 38% lower gravity compared to Earth. Or the gravity is 38% of the Earth. In terms of the temperature is much, much lower compared to the Earth, and it's fluctuating a lot between night and day. The amount of solar energy is 43% of the Earth form, which is much lower because of the distance from the sun. There is no atmosphere, and it means very harsh radiation condition for staying on Mars. And the type of atmosphere which is available on Mars is completely different than Earth. 95% carbon dioxide and just 0.4% oxygen. It makes a big differences between Earth and Mars in so many ways. But still, compared to other planets in the solar system, it's the first priority that has been considered so far in most of the space exploration research. And the Martian surface is covered by very fine regolith material and is covered with vast expansion of sand and dust. and its surface is also considered have some sort of rocks and boulders. Through different NASA research by sending different rovers like Curiosity, Spirit, and also Opportunity rovers, they study the chemical composition of the available material on the Martian condition. They also show some evidence of the water molecule in the frozen state, some sulfur, chlorine, and also some organic compounds as well. So the thing that I'm going to review in the next slide is all returned back to NASA Centennial Challenge, where NASA invite industry and also academia to push the boundaries for adoption of 3D printing in the construction. So the main reason was because this industry has lower adoption. They wanted to speed up the use of 3D printing for Earth projects, firstly, and learn more experience about how we can train robots to do the construction of the Earth. And the second was just have more advancement in terms of colonizing a space for the future. So they designed multi-phase challenge. They invited industry and also academia to be part of this challenge. I'm going to review part of the different phases of this project. Penn State was part of this project for 3 years at different levels, and I'm going to quickly review some of those advancements. So whatever I'm presenting in the next slide is from the Penn State team that I did during my PhD and postdoc with a big team of the faculties and students all around the campus. So it was completely a teamwork. We have an interdisciplinary team of engineers and also architecture work together to make this NASA project happen. And it was a great teamwork. We work on 3 different areas which are all involved in 3D printing, from material to the system, to the design. We try to study each of these aspects separately and also design and define the interrelationship between all these 3 aspects in the 3D printing to be able to address the larger scale printing. And at the time that we were doing this project, there was no company or other industry who are doing larger scale 3D printing. We were one of the few first entities who started this type of research for larger scale 3D printing. So when it comes to this NASA Centennial Challenge, the first phase were all about material. So if we want to colonize Mars, and it was the focus of this NASA Centennial Challenge, were on Mars. So when we want to colonize a space, it doesn't make sense to transport material from Earth to space, first of all, because of the distance, and secondly, because we are colonizing a space to take the advantages of the extra resources there. So we need to find a way to use the indigenous material and resources available on Mars. So if we return back to 3D printing for the Earth project, as you recall, I mentioned concrete and soil. Local soil has high potential because they have plastic properties. They are formable. We can form them to different shape in their early age before they get hardened. So they have high potential to be used for the Earth project. But when it goes to the construction on Mars, we need to design the material from the indigenous resources that's available there. And the first level of phase 2 of NASA project was all about the design of the indigenous material that we can produce on Mars. But before going over what are the options, I want to just review what is concrete first. So concrete is all about small rocks that they are held together by some glue. Right? So it's in the easy way, we have tiny rocks, it would be sand particles, it would be gravels. They are held together by proper binder or glue. This glue material could be clay. So for so many years, for 1,000 years, humans used to use clay as a construction material. Or during the Roman construction, they use the ancient concrete from their local resources. And nowadays, we are using the conventional concrete for the construction, which is made of small rocks, as I mentioned, plus the glue. And the glue that we are nowadays using in the concrete is a combination of cement, which is an inorganic material, plus water. So cement and concrete are two different terms. Sometimes we use them interchangeably, however, it's not correct. Cement is one of the materials which is used to provide binding property and hold the aggregate together to form the artificial stone or concrete. So now that we learn about this, let's see what is available on Martian condition. So the NASA study showed that the Martian crust, about 30 to 100 kilometer thickness of the Martian crust is consisting of volcanic basalt rock. And these rocks are very similar to the rocks that we have on the Earth. So if we can extract this material, we can use it as an aggregate for construction. So we have aggregates or tiny rocks, but the only remaining part is designing the right glue to hold them together for the construction. So if we can discover the appropriate Martian binder, we could produce the Martian concrete. So we need to design some sort of Martian glue that hold all of this basalt aggregate together, and we can make the Martian concrete from the indigenous resources there. So in order to design the Martian concrete, we studied the soil composition from different rover study that NASA just published. So these are the result of 3 different studies from different soil samples, and it shows that Martian soil is slightly alkaline. They find also some sort of kaolinite, which is some clay that we have also some sort of this material on Earth. And it also holds sodium and silicon compounds. They also find about 2% of frozen water on the regolith that they study during their exploration, Mars exploration. So by having all of this information, NASA asked the team to design some binder or glue that we could use for Martian construction. So as I showed in the previous slide, one of the material which was abandoned was magnesium oxide, oxychloride. So one of the binder that we tried to design was called solar cement or magnesium oxychloride cement. So in this system, we were able to make a very strong binder, which is capable to hold aggregate together. However, when it goes to the 3D printing process, this material set very fast, sometimes inside our machine. It just damaged our system. Because of that, we give up on using this material. Still, there are ways to adapt this material for construction, mostly by using some sort of additive to postpone the chemical reaction between the material and have a larger setting process for this material. We are not able to produce cement on Mars because of some reason. First of all, the calcium compounds is very low, and in order to make cement, we need to calcine this material at very high temperature. So in order to make cement on Earth, we heat up the limestone to the 2600 degree Fahrenheit, which is 1/3 of the temperature of sun. So we need to apply higher energy, and considering the distance between sun and Mars, it's very hard to convert the limestone to cement. So cement is not the right material that could be used for Martian construction, and because of that, we are studying different glue. Another glue that we considered was geopolymer-based material. This is also part of the study that I previously did. It's called cement-free concrete. In this type of system, we are using some sort of aluminum silicate source material, and as you see in the previous slide, we have large resources of aluminum silicate precursor on Mars condition. This material cannot be activated by just water. we need to use some alkaline solution to break the bonds between the silicate and aluminum, and in order to make the glue, we need to use some alkaline agent. So there are two different types of this material. I'm not going to details of design of this material, but we work on one part or two-part geopolymer for this project, and we deal with different types of the way to activate this material. So we're going to use, in this study, we used basalt as an aggregate, and because kaolinite is the material that they find in a special location on the Mars surface, we try to calcine it at very low temperature and make metakaolin. So metakaolin is another material that we can process it on Earth, and it could be used and activated by high alkaline materials. So because of the Martian regolith holds alkaline compounds, and for this project, NASA allows the team to use the frozen water on the Mars. So we assume that we can use that water also to make the glue. So we were able to design some binder or glue-like material for the construction on Mars. These are different studies. We designed like 8 different types of two-part geopolymers. We printed some part with that material and 4 different types of one-part geopolymer. And finally, we just pick the material that has highest potential for printing and resulting the best quality and strength at the end. So these are some of the studies that we did in the material side in order to be able to activate kaolinite and make it a binder and glue for this material. So we were able, for this phase of the NASA project, to design Martian cement. We call it Marscrete. And these are the material that has been used in order to develop this material. So this is the very first part of the very first phase of NASA Centennial Challenge in 2016. At the time, everything was very manual in our team. So as you can see, all of the people are working around the tiny robotic arm. We had everything in smaller scale, and we were other than material, we need to adapt our system for the material, and this is the system that we started our printing, but over time we advanced the system to be able to print larger scale. So these are some of the pieces that we printed for the level 2 of phase 2 NASA Centennial Challenge in March 2017, and we were able to we won the second place award for these pieces. We printed the cone, we printed the cylinder and beam, and we measured the quality of print, the strength of the material, and some other aspect, believe me or not, to be able to print one of these cylinders. We were working for 5 months in the lab, and finally we achieved the best result, and we were able to advance our system over time. And in the last level of phase 2 NASA project, we were able to 3D print a dome with the cement-free material that we designed, or Marscrete that we designed for this competition. The material property were also measured in the head-to-head competition in the Caterpillar Visitor Center in 2017, and we also awarded the second place in this head-to-head competition. Because our system, the temperature of the material was a bit high, we tried to design some cooling system to make sure that our material could be nicely printed. Then we started third phase or last phase of NASA Centennial Challenge. In the first step of this challenge in 2018, they asked the team to 3D print a slab. The main goal of the last phase of NASA Centennial Challenge was increasing the automation and coming up with some autonomous construction, because it was the main goal to minimize the human involvement during this project. And because of that, they encouraged the team to minimize their involvement during the construction process. In the second level, we also printed the system, the cylindrical tank. We measured the hydrostatic stability of the printed material, the quality of the printed material. We printed this tank in less than 30 minutes. It was very fast process. And we achieved, again, a second place award in this level of NASA competition. Finally, in level 3, they asked the team to for virtual construction to design and build sustainable shelter for humans to live on Mars. So they asked the team to design 1,000 square feet of living space for 4 astronauts. It includes the life support, MEP, safety, entry, and exit system. I don't know if I have time to show this video or not. I might just skip it, but this is the virtual construction that Penn State team did with a team of artists that helps us to make this nice video as part of this NASA challenge. I'm gonna skip it, but I will share a link with Chip to share with the team if it's feasible because of the timing. So the last level after this was 3D printing of larger scale, of 1/3 scale of the habitat that we designed. We scale up our system to be able to achieve the automated construction. This is the system that we designed, and everything was just fully automated. We had 2 robotic arms to take care of the construction and placing the opening. All of the crew and construction people should just monitor the 3D printing process. We weren't allowed to touch anything during the printing process, and it was the very last phase that we were able to 3D print larger scale. And again, at the time, there was no other industry in 2019 who were doing the larger scale 3D printing. We were the few first ones who achieved this larger scale printing in this scale. So I'm going to just show you the Caterpillar Visitor Center and head-to-head competition. The competition took place in 3 days, and the team had 10 hours per day to 3D print their structure. Unfortunately, we come up with some system problem during the printing process that slowed down, and we damaged part of our system, but finally we were able to finish our 3D printing. I don't have time to show this video. It's a very nice video of the process, but I'm going to show this video, the short video by NASA as a result of this competition. So among 60 teams, just 2 teams make it to the head-to-head competition at the end. The first team was Penn State from academia, and the second team was from industry. Try to remember the name. Yeah, it was Space Factory from New York, AI Space Factory. So the entire printing process should be done automatically with no human involvement. There were so many judges around the construction area to just see if there is any human involvement during the construction process. And Penn State were able to finish the construction because of some system problems. We lost some points for the autonomous construction, and then we have the impact test, the leakage test, and crush test to find the weakest part of the structure. And the structure that we built up in 3 days, it was just easily crushed in some seconds. But eventually we were able to achieve another prize. So in total, Penn State won about $500,000 at the end of this competition. It was very great deal for our team at Penn State. I learned a lot from the teamwork especially, and I'm going to very quickly review some of the future work for the construction in the space. So currently, the main goal of the NASA is construction some habitats or settlements for the human on Moon from the Artemis project. The main NASA center, which is work on this area of the research, is Marshall Space Flight Center. I used to work with some of the folks from this MSFC during the NASA Centennial Challenge, and it was a great experience to work with them, but they are pushing all of the boundaries for robotic construction, so we need to design a system which could just make decision on its own, because there is no human on during the construction on Moon, and also they are dealing with the material and resources. So another area is waterless concrete, because it's very hard to deal with the water where the pressure is very low, where the gravity is very low, and the temperature is different. So because of that, the NASA encouraged the teams to think about waterless concrete. So one of the resources is sulfur concrete. So sulfur is the 11th element in terms of abundancy for the Moon, and for the Mars, there are more of these resources available. However, because the melting point of this material is very low compared to lunar regoliths. So the melting point is 239 degrees Fahrenheit. However, this melting point when it comes to regoliths is about 2,500 degrees Fahrenheit. So it's much, much lower. It's a great resource when we talk about waterless concrete or some construction material. So part of the NASA research is all about if we can find a way to 3D print sulfur for construction on Mars. Additionally, they invested about $60 million for one of the 3D printing firm. It's called ICON, for further research into the technology to build up the autonomous construction for habitation of the lunar surface. They also granted about $20 million for 3 companies to work on the development of solar panel, the prototype, and also do some environmental testing to make sure they could achieve the maximum energy from their solar system. And they are pushing all of the boundaries to make sure by 2040 we are able to start our first step for human polarization of the lunar system. And this is part of the ICON 3D printer that printed about, I guess, 2 years ago in Houston. It was in the NASA Johnson Space Center with the 3D printer. During the printing process, there was no human involvement. Everything was processed by the machine. This is the ICON machine. And they use this mission to provide valuable insight and information to assess NASA's space food system, as well as physical and biobehavioral health for astronauts. So this is another part of the research that's going on currently in Houston in the Johnson Space Center. So I'm going to just quickly pass all of this slide. This is some of the research that currently I'm doing. We are doing different types of printing for sustainable material. For local resources, you can see the nice dome that we printed from the local resources in New Mexico. And I believe UNM has high potential to do this type of research, especially because of the CASA project that CHIP is running, and we're going to have more information about available resources on Moon over this proposal. Additionally, we have the Grand Challenge team who are working on different aspects of a space project, and it gives us the potential to form a nice team, interdisciplinary team of different researchers around the campus and bring this opportunity to our campus. Thank you for your time. Sorry that it takes longer than what it was supposed to be.
Are there questions online for Maryam? Should just raise their hand, I think.
Could you ask your question? I'm trying to see the name. Kerry, please.
Hi, yeah, thanks for the talk. It was really interesting, and I work mainly on the Moon, but I really loved the bit about how exciting this is on Earth as well. So that was really cool. But I have a question about seismic hazard. And I think if anything, it applies more to Earth. You know, how do these materials stand up to seismic activity? And also, if they get damaged, can they be repaired?
So it's a very great question, especially because the seismic response of this material is a very important matter when it comes to the Earth project. So because it's very new technology and we are talking about layer material instead of like the concrete material that we used to use, There are so many researches going on to learn about the response of this material to the lateral force. Currently, Texas A&M is one of the universities who are invested a lot on this type of research, and we're going to use it for also the space project. What was your other question? Sorry.
It's to do with if it's damaged due to a quake.
Right. Of course, yeah. Self-healing is also another thing. There are so many teams who are working on the self-healing concrete for the Earth project. And if we achieve success, again, these are very new recent research that they are going on. I'm also part of that project. If it succeeds for the Earth, we're gonna expand the horizon of this type of research for the space project. Yeah, thank you. These are two important aspects of 3D printing project. Currently, there are so many research teams working on different areas, especially in this two area that you mentioned.
Cool, thank you. It was a great talk.
Thank you so much for your attention.
Are there other questions for Maryam online? Any questions in here?
I just have a comment. I saw that you have a cistern.
Mhm.
Be interesting to know how each of these materials would affect the quality of the water over time if it were holding water in a cistern.
Oh, you mean in terms of if we get some ions or some material? Yeah, again, there are some environmental team who are working because these are not cement. These are different materials. Some of them are made of base and they have heavy metals like mercury or something else. So there are some teams are working on the leaching from these material into water. However, up to my knowledge, there is no leaching from the damaging or those agents into the aqueous system. However, there are so many researches going on. Maybe I need to update my knowledge also, but up to the level that I know, they didn't see any pattern of the leaching of the material. Thanks. Yeah.
So early on, you showed these mud printed houses.
What's that question?
Early in the program, you showed these mud printed houses.
Right.
I'm wondering do they use a binder or is it just clay or?
It's just the local soil. And it's the same thing that's really, that's UNM. I guess we're showing one of the slides here. So the dome that you see here is just a local soil. We've mixed it with water and printed it. But in terms of material property, this is the research that I'm doing with my team. We need to address some of the problem in terms of shrinkage because the clay has the potential to swell and then shrinks. So we need to address those problems to make sure this is the right material for affordable houses. But this is very sustainable green material instead of cement that needs to be heated up to very high temperature, release large quantity of carbon dioxide to atmosphere to make a binder, but this is local resources. It doesn't need any extra processes. So we prefer to use these sustainable resources.
We have a question online from Tony Gargano.
Yes.
Hey, Miriam, that was great. A question for you about binders. So I think a lot about water production on the moon, and I'm just curious, what is your thinking in terms of the best binder material for regolith to make these structures ultimately? Are you thinking water or some other compound?
So as I mentioned in part of my research, in part of my presentation, there are two different approach. One is the concrete, which is made of water, and the other one is waterless concrete. So for the waterless concrete, currently there are teams who are working on the use of sulfur because it has very low melting point and we don't need to use water, especially considering the pressure on moon, the gravity on moon, and all other conditions, which is much, much different than Earth. Maybe waterless concrete is better approach, but if we want to use sulfur, we should make sure it's abundant, available there. And if we want to use regolith, again, we need high amounts of temperatures, 2500 degrees Fahrenheit, to achieve the melting point of this material and to be able to form this material. So there are some big problems that we need to address in terms of energy, But there are so many researches going on currently to see what is the best method, especially considering the abundance of different resources on Moon.
And to follow up on that, do you expect any interactions between the regolith material and this sulfur-like binder if you were to use that on the Moon that would influence the material properties ultimately?
So the current project which is going on is with one of my colleagues in LSU. He is using sulfur, molten sulfur as binder and mix it with the regolith, lunar regolith to form the concrete. So far his research shows so much promises, and because of that NASA also funded his project to learn more about the system and see if it is viable system to be considered as one approach for construction. But still there is no like a strong publication on to see and study the durability of this material, the permeability of this material. It could provide great protection, especially for radiation when it comes to the Moon or Mars with very thin atmosphere. So there are so many other research areas that needs to be addressed when it comes to this space project.
Awesome, thank you.
Thank you.
Great, thank you all. It's at the top of the hour now, and it's time for us to draw to a conclusion. I just want to thank Maryam again for her presentation. It was a different perspective than what we're normally have in these seminars, but an important perspective. Thank you, Maryam.
Thank you so much for your time. It's a pleasure to be here today.
I just want to remind everybody online that next week is the Lunar and Planetary Science Conference, and so we will not have a seminar in next week, but 2 weeks from today we will. So keep posted, and I will post the speaker and the theme of the presentation. Thank you all again for joining us. Bye-bye.